The commercial name for PTC is RTD. Let me just, write it with black color. So RTD is the commercial name for PTC, which stands for resistance, temperature, detector. On the other hand, we have the commercial name of thermistor for these devices. So I can just, write thermistor for NTC here. So the time that you just hear this name, you know that this one is the commercial name for NTC. The most famous RTD at the side is shown by PT. So it shows by PT. PT stands for platinum. So if you have, for example, copper, you can just show it by Cu, or if you have, for example, nickel, you will be able to just show it or explain it by Ni. But as I mentioned, that the most famous one would be called as the PT one. We have different types of PT in the industry. Starts from PT 50, and after that 100 by 100, it just goes up to 1000. In this group that I just wrote for you, two of them again are more well-known or more famous as compared with the other ones. These two things actually are PT 100 and PT 1000. I can tell you that for the range around up to 350 or 400, we just use PT 100 because actually in this range, I mean up to 350 or 400, the curve of this the curve of this device is totally linear. So I can tell you that the prediction of the possible, changes in the foreseeable future for device is totally, carry out better than the, for example, other items. So do not forget, for temperature less than this amount, try to use PT 100, and PT 1000 actually even you can use for more ranges too. For example, up to 7 or even 800 degrees of centigrade, we can just use PT 1000. But again, I can just tell you this one, for the temperature, which is more than this amount, we prefer or we tend to use the thermocouple, because thermocouple are a little bit accurate or precise in higher temperature. Moreover, they are cheaper and actually widely used as compared with, for example, PT 1000. So I can just put them into different cases. The time that you have the temperature less than this amount, you just focus and concentrate the usage of this element, and the time that you want to, for example, reach and measure upper temperature, thermocouple is going to be a best solution. So I can just draw something, because I mentioned something for the curve of these devices too. So I can just draw something. It's the temperature based on, for example, degree of centigrade, and actually this one is the resistance of the material, which is just based on the ohm, the unit of its ohm. So we have this one here. Can you see this one? It's something just like it. It's for a PTC, or RTD1, up to, for example, 350. We will be able to have a linearity of the curve too. That's for sure. For any types of change here, I can just guess about the thing that's going on after that. But for NTC, we have this one. This is the curve for NTC. It's a little bit actually not linear as compared to the previous one, but I told you, the resolution of changing of this one is really better than the previous one. It means that, for changes of the resistance, we have just 0.5% per 1 degree of centigrade increase. Okay, so Let's back to this part, please. Maybe you want to ask me some questions about the numbers that I wrote for you on the whiteboard. What are these numbers standing for? Okay, so let me just draw an example here. When I say PT100, it means it's a type of sensor which has been made by platinum, and in 0 degree of centigrade, it shows 100 ohm. So now you know this one. What does it mean? So it means that for 0 degree of centigrade, for this element, we will expect to have 1000 ohm. And it's totally true. And here, for each degree of centigrade change, 0.385 ohm would be changed. So you can get a result that when we reach to 100 degrees of centigrade, see this one please? If we just reach to 100 degrees of centigrade, that for sure we have 138.5 ohm. Actually, no, I didn't do, for example, some difficult things. I just, multiply this one with 100, and I reached 38.5 ohm changes. So I just add this amount to 100, and it's a thing that you can see here as well, 138.5 ohm.